I began the first part of this two-part series on vacuum tubes and electron tubes showing the inside of an SX62A that I am restoring. That's a Hallicrafters. But for this part, I'm going to use as my model this Philco 38.4. One reason I'm using this is one of the radios I mentioned in the first part that my Uncle Jimmy bought me to work on. It was my first shortwave radio. It didn't work when I got it, and I was able to get it working. It was a really minor problem with a grid cap that just was unsoldered. But the other reason I wanted to use this one is because I would also like to dedicate this second part to my brother and his wife, who rescued this receiver. After I went in the military following high school, I lost track of a number of items that I had left at my parents' house, among them this receiver. Well, years later, my brother and his wife presented me with this receiver. I thought it had been long lost. So anyway, I'm going to use this as the model for the circuitry in this part, which is going to be devoted primarily to tube circuits. This is the schematic of the Philco model 38.4, and I'm going to use it, as I said, as a model for the tube circuits. But when I say as a model, just as a kind of context to show how these various circuits work together to produce a useful result. Now, whether you're interested in tube circuits because you'd like to understand how your tube hi-fi amp or your tube guitar amp works, or you're interested in old radio or old television using tubes, or you just are generally interested in tube circuits and vintage electronics, this should be applicable to all of you, because most of these circuits are used in one form or another in a lot of those different applications. Now, previously, in the section on how tubes work, we talked about rectifiers, that is, single and dual plate diodes that are used in half-wave and full-wave rectifiers. So I'm not going to repeat that. Instead, where I'm going to begin is in the audio amplifier section with the audio amplifier and the audio output. Now, this is the audio amplifier tube. These are the audio output tubes. This is the audio output transformer, and then over on the far right you see a depiction of the speaker. We're going to primarily focus on this circuit, which is a push-pull circuit. You can also have single-ended circuits. If you divide this circuit in half and divide the transformer in half, in other words, only use the bottom half of the transformer and a single tube, you get a single-ended audio amplifier. Those are not as powerful, nor are they as free of distortion. Push-pull amplifiers have an additional advantage. Not only do they produce more power because they're using two tubes, but also they produce less distortion because they are balanced. And so distortion signals that are equally balanced on both sides of zero will be balanced out by a push-pull amplifier and will not appear in the speaker. We won't talk much about distortion in this section or even in this video, but distortion is an important part of amplifiers. So let's now talk a little bit about the audio amplifiers, push-pull, and then we'll come back to this circuit and I'll show you something that's a little bit unique. This is not a standard audio amplifier push-pull. And those of you that have seen push-pull before will recognize there's no phase inverter in this circuit. There is phase inversion, but no explicit tube devoted being a phase inverter, nor is there a transformer used for phase inversion. So we'll come back to that after we know a little more about how push-pull amplifiers and audio amplifiers in general work. Here is a transformer coupled amplifier, and many people find transformer coupling to be the easiest to start with, so that's where I'm going to start. Over on the left you see depicted a sine wave. Sine simply because it follows the amplitude relationships of a sine, that is a trigonometric figure. I told you we wouldn't go into math beyond add, subtract, multiply, divide, so we won't talk about sines and cosines and so on, but this is often called a sine wave because of its shape. It is the input voltage. This is normally called the preamplifier, or sometimes just the amplifier, and this is usually called the output. In this case we're using triodes, and a transformer is being used to couple the output of this tube to the input of this tube. The input, of course, is applied to the control grid. The cathode is connected to ground through a resistor, and in a little bit we'll talk about bias networks, but this is part of a bias network. Furthermore, a capacitor is connected across the cathode resistor. This is called a cathode bypass capacitor, and its purpose is to improve the frequency response of this stage. Once again, we'll talk about that, but not just yet. Then the output of the tube, in this case, is coupled to a resistor. It might also be a transformer to a speaker or others, but this is basically a two-stage triode amplifier with transformer coupling. This is an equivalent two-stage amplifier using pentodes. Once again, we'll talk about the basic elements. There is a cathode resistor in this pentode's cathode and a bypass capacitor. The screen grid is connected through a resistor to the positive or B plus voltage, and then there is a capacitor to ground off the screen, normally called the screen bypass capacitor. There is also a resistor connected from B plus to the plate. Usually this is called the plate load or the plate resistor, and a capacitor that connects the output of this tube to the input of this tube, normally called the coupling capacitor. There is a grid resistor on the control grid of this pentode. There might be a small capacitor here for reasons we won't talk about, but it's shown in dotted lines because it often is not present. This pentode once again has a cathode resistor, which is bypassed by a bypass capacitor. The screen grid once again is connected to B plus through a resistor and bypassed through a bypass capacitor, and the output is connected through a resistor to B plus, and the total output is taken between this point and ground, or B minus. Once again, we haven't talked about a few things in either of these two circuits, the one with triodes or the one with pentodes, and we will cover those in just a minute. But before we move on to the specifics, let's talk about a third type of amplifier circuit. This is an output circuit, often called a push-pull. It, in this case, uses triodes, but you could once again use pentodes. There is an input signal to this grid and an input signal to this grid. Now, normally, these two signals are the same signal inverted. In other words, this is the positive going part of that signal, and this is the negative going part. In other words, as this one is going positive, this one is going negative. They are the inverse of one another. For purposes of simplicity, we have shown the bias supply as simply a battery, and we'll talk about bias circuits in a minute. The bias supply is designed to hold the grid at a particular value relative to the cathode. The plate supply for both tubes is this battery. Once again, in a real amplifier, it would probably be a power supply, perhaps a half wave or full wave power supply. And normally it is connected to the center of the output transformer. Each plate is connected to a corresponding end of the primary of the output transformer, and then the load is connected to the secondary. Normally this is a speaker. You may recall that you can use pentodes in this circuit. You also can use beam power tubes. And one of the things that we'll see a little later is that the SX62A that we have been restoring uses beam power tubes, whereas the model that we're using for this tube circuits video, the Philco 384, uses pentodes in a somewhat unusual arrangement. Here you see a combination of tubes used in a speech amplifier circuit. Now, this particular circuit is a general circuit. A microphone is chosen as the input here, but this could be a record player, it could be a guitar, it could be a number of different sources. Normally there is some kind of resistor-capacitor network on the input that shapes the tone characteristics of the amplifier. We'll talk about that much later, but in this case it's just shown generically. There often is an isolating resistor between the tone compensating and the grid, and sometimes there's a second capacitor designed to produce additional tone compensation on the input. This network is sometimes called an equalization network, and you might see, for example, if this were a phonograph, this might be the RIAA equalization network. RIAA just stands for the Recording Industry Association of America, and it's a definition of a particular frequency characteristic, a particular curve, that works properly with the pickups of most phonographs. We won't talk about equalization here, but be aware that these do exist, and they are important in certain applications. So the signal is applied to the control grid. The cathode, once again, through a cathode resistor, bypassed by a bypass capacitor. Once again, the screen connected to B+. In this case, it's connected through two resistors to B+, and then bypassed to ground. Sometimes this is done to further isolate the screen from the B+ supply, that is, this extra resistor. There also is a resistor to the plate, providing B+ to the plate of the amplifier, and then a coupling capacitor to this device. This is a volume control, sometimes called a potentiometer, but nonetheless a volume control where the full signal is applied to the top, and then by turning the volume control you can select everything from ground all the way up to full signal or anything in between. That signal is then applied to the grid of this voltage amplifier. Once again, cathode resistor bypassed. Plate, in this case, is connected to B+ through a transformer. B+ is bypassed to ground. The output of the secondary of the transformer is a center tapped transformer. So this tap will be out of phase by 180 degrees with this tap. In other words, they will be inverses of one another. As this voltage rises, this voltage falls, and vice versa. So one phase, in other words, the rising phase, let's say, is applied to this grid. The falling phase is applied to this grid. Now understand, after it's gone through a half a cycle, what was the rising phase here is now the rising phase here, and vice versa, but we will simply refer to this as the rising phase, meaning the one connected to this transformer lead. There is a capacitor across the transformer. Once again, that is to provide some frequency equalization. And the output of these two tubes is applied through this transformer with B plus at the center tap, an equalizing capacitor across, and the cathode, once again through a resistor to ground with a bypass capacitor. So the way this circuit works, of course, is this amplifier is primarily designed to match the microphone to this voltage amplifier and to provide equalization and a small amount of gain. But it's mostly a matching amplifier. This provides most of the voltage gain, and these two provide most of the power gain. Now, power is voltage multiplied by current. So these not only provide some voltage amplification, but they primarily amplify the current through this transformer. And so with the combination of the voltage gain of this stage and the current gain of these push-pull triodes, you produce a power output that is substantially greater than the power input. You may notice up here that this is called a Class AB1 power amplifier. We're going to talk about that in a little bit. That has to do with how this stage is biased. Here is a summary of the different ways that signals are coupled from one tube stage to another. The first is a simple resistance-capacitance coupling. There's a resistor in the plate of the preceding tube, a resistor in the grid of the following tube, and a capacitor couples the two together. You can achieve the same result with a transformer, where the primary is in the preceding tube, the secondary is connected to the following tube. A second or third coupling method is what is here called push-pull. The reason that it's separated from the transformer coupling is, in this case, not only do you have transformer coupling on the output, but to provide the phase inversion, it's using transformer coupling on the input. You can also couple using impedance coupling. Instead of a resistor in the plate of the preceding tube, you can have an inductor. And, for example, at higher frequencies, especially at radio frequencies, this inductor is much more efficient than a resistor because it provides high impedance to the frequency you're interested in while not reducing the voltage on the plate as much as a resistor would. So you'll see these in RF stages, particularly power stages of RF amplifiers. Here is an impedance transformer coupling. You'll notice that there's an impedance in the preceding stage, and a transformer is used in the following stage to provide phase inversion, and the impedance is coupled to the transformer with a capacitor. Here is a resistance transformer coupling, where you simply replace the impedance in the preceding stage with a resistor. Once again, a capacitor connected to the transformer, and then the transformer is providing a transformer coupling to the following stage. A yet further way of coupling is called cathode coupling. And in that, what you are doing is, it may be a little hard to see here, but the cathode of this tube is connected to a resistor. This cathode is connected to ground. So, I'm sorry, to B+. The plate is connected to B+. The plate of this is connected in an RC network just like the one up above, but you notice that the cathodes of both tubes are connected to this resistor. That causes the bias, or the operating point of this tube, to move, the second tube to move in conjunction with the first tube. And although we're taking the output off of the plate, what is actually happening here, this is a somewhat unusual, and you don't see this very often in modern circuits, but in some old stuff, particularly pre-war, you see a lot of cathode coupling, because it was a way of coupling from one tube to the other by using a common cathode resistor. And finally, you have direct coupling. Now, direct coupling is used where you have to preserve the DC, or direct current, value. An instrumentation amplifier, for example, might be direct coupled, the purpose of which is to provide the actual DC level of the input to be coupled to the tube, to the next tube. One problem with this kind of coupling, however, is that the voltage levels build up, and at some point you have to either switch over to capacitive or transformer coupling, or you have to provide some kind of biasing network that pulls the voltage values back to within the normal levels of the tube. We aren't going to talk about instrumentation amplifiers, but where you see direct coupling, you can almost always bet that it's an instrumentation application, like an oscilloscope, for example. Now let's talk about bias. And bias, for now, we will simply say, is the way of establishing the voltage on the grid with no signal. In this case, that's done with a battery. So this is often called fixed bias, where the input resistor is connected in series with a battery, so that the bottom of this resistor is at the battery potential above ground. In this case, it's below ground because it's the negative lead of the battery. So that provides a bias of negative voltage. In this case, this says it's a 5-volt battery. So that means there's negative 5 volts on the grid relative to the cathode. We'll talk about why we want bias in a little bit. A second way to provide bias is with a cathode resistor. Current flowing through the tube flows through the cathode resistor. In doing so, if the grid is connected to ground, the current which flows through the resistor produces a positive voltage on the cathode. That has the effect of making the grid, which is at 0, negative relative to the cathode. Often when you use cathode bias, you put a cathode bypass resistor, a capacitor, across the resistor for reasons that we will talk about when we get to frequency response. A third way of providing bias is what is called grid leak. And grid leak is where you allow current to flow out of the grid. During the charge cycle, that is when the input is more positive, this capacitor becomes charged. When the signal drops below the charging level, the capacitor tries to discharge through this resistor, and that causes the grid to be slightly negative. if the time of the capacitor resistor discharge is long enough relative to the signal, you will build up a negative voltage on the grid relative to the cathode, which is grounded. And that is known as grid leak bias, because basically you are leaking current off of the grid to provide the bias current. This is another type of grid leak in which you are providing a large resistance and the grid itself is actually floating. And then you provide a capacitor to store charge during part of the input cycle. When you apply a voltage, some of that voltage is stored in this capacitor, and when the signal drops down, that level is maintained relative to the input as a negative bias on the grid. You don't see grid leak bias very much anymore. It used to be used a lot, particularly in the 30s and in the 20s. Most of the bias that you will find today in amplifiers, whether it's radios, guitar amps, hi-fi amps, or whatever, is cathode bias, which is what's shown up here. We've talked about how we can generate a grid bias. Now let's talk about why we want a grid bias. Let's assume that this is the input signal on the grid, swinging from this point to this point, with this being ground. If this is the current of the tube, in other words, for any particular grid voltage, this is the amount of current that the tube will conduct. So when there is zero bias, it conducts this amount of current. As we apply negative bias, the operating point, in other words, the point at which the ground or 0 volt input puts the tube, moves to this. In other words, it moves from here down to there because the grid voltage moved from here over to here. At the operating point, if we apply this signal, we will get an output signal that looks like this. Now, if the line, the current that is line from this point to this point, is a fairly straight line, as it is here, the output will be a fairly faithful reproduction of the input, only if it's an amplifier, it will be a little bigger, maybe a lot bigger. But if the input signal gets very large, for example, if the input signal drives the tube, the grid all the way down here, the tube will cut off. If you drive the tube too far to the right, in other words, too positive, the tube will saturate. And we'll look at that in a minute. This type of application is called a Class A amplifier. And it's called Class A because it never moves near cutoff or near saturation. It always stays in what you would call the linear region of the operating curve. This, on the other hand, is Class B operation. In this case, we operate the tube at cutoff. The positive half cycle takes the tube out of cutoff and drives it to about the middle of its range. But the negative half cycle, since it's beyond cutoff, doesn't do anything to the tube. It just holds it even more cut off. As a result, instead of getting a nice sine wave at the output, you get current pulses. This pulse becomes this. This pulse becomes this. And the area here is the missing part at the bottom. So in other words, the tube voltage on the grid is moving from here to here, back to here, and then all the way down to here and back to here. That causes the output to vary from here up to there, and then back to here, and then stays there for a while, and then goes back up and back down, and that's what produces this output. Now, if you're trying to reproduce something like speech or radio music, anything that is relatively linear and you want very little distortion, this is not a desirable operation. But if you're trying to produce a large signal, like a code signal for sending Morse code over radio, this might be a very efficient way. And the reason is that for half of the time the tube is operating, it isn't conducting any current. That is, down in this region, this time down here, it's not putting out any current. So this tube operates cooler than a Class A tube would with the same output level. And if you're not interested in a distortion-free environment or a low distortion amplification, you're just interested in lots of power, this is a good way to do it, Class B. Between Class A and Class B is Class AB. And AB means that the tube conducts for most of the cycle, but not all of it. Remember, in Class B it only conducts for half a cycle. Here it conducts for more than half a cycle, but not for the full time. And Class AB operation is divided into that situation where the tube conducts for more than 50 but less than 100%, and the grid does not draw any current. That's called Class AB1. Class AB2 is where it operates for more than 50% but less than 100% of the cycle, and the grid does draw current. This is Class AB2. Why might you use these? Well, it turns out that if you operate an output stage in Class AB1 and it's a push-pull output stage, the distortion produced by this is offset by the fact that during this time the other tube in the push-pull arrangement is conducting while this tube is cut off. And the result is a fairly low distortion output, even though each tube itself is distorted pretty badly, but the sum of the two is a fairly distortion-free output. Not only do you get the efficiency of Class AB operation, because each tube gets to rest, if you will, for a short period of time during the cycle, but you also get the high power output, and in push-pull you get very little actual distortion. The final class of operation that we'll talk about is when you bias the tube into cutoff. That is, you bias it so far negative that only the peaks of the input signal turn the tube on. This is called Class C operation. It is the most efficient operation. That is, you get the most power output from a Class C amplifier. But it also produces the most distortion, because not only is it not reproducing the negative half cycle, it's not even reproducing this part of the positive half cycle. So what happens is the tube is biased here. During most of the operation it remains below cutoff. Only when the input signal is fairly positive does it come out of cutoff and move up to this point, producing this output. And then it very quickly falls back below the cutoff point, shutting off the tube for a substantial part of the operation. Normally in Class C operation, the tube operates for less than 50% of the cycle. Returning to the Philco 384, normally the first audio amplifier is operated with either zero bias or very low cathode bias and a large grid resistor. The reason is that the input signal is relatively small. You don't need to bias this stage very much to keep it in Class A operation. And as a result, You do not dissipate a lot of heat in this tube due to what is called quiescent current. Quiescent current means the current that the tube draws when there's no signal applied. But this stage normally operates Class A. It then feeds this stage, which is a somewhat unique push-pull amplifier. I say unique because you may notice it neither has a phase inverter tube like the SX62A has, nor does it have a phase inverting transformer to provide the grids with opposing values. Instead, it uses a rather unique circuit. You notice that the screen grid of this tube is connected through a resistor to B+. This screen grid is connected directly to B+. The screen grid is coupled through this capacitor to this grid. So the output of this tube is coupled to this tube. As this tube operates, its screen grid drives this tube. Without getting into too much of the detail or the mathematics, the screen grid is 180 degrees out of phase with the grid, the control grid. So, in essence, we're using this output stage to provide the phase inversion for this output stage. Normally, push-pull operate in Class AB1 operation. In other words, this tube is a little bit cut off and this tube is a little bit cut off at the normal stage. As this tube begins to conduct, this tube cuts off even more. But they both are conducting. In other words, it's in Class AB1 operation. It provides more efficiency, more power output, and because of the characteristics of a push-pull amplifier, that is, it cancels the even distortion, you actually wind up with a fairly distortion-free output on the speaker. Let's now move and talk about a few more. Now, you probably recall that in the first portion, how tubes work, we talked about using a detector or a diode as a detector. So we won't talk about that. Instead, we'll move on and talk about how we do IF, or intermediate frequency amplification. By far, the most popular tuned amplifiers using electron tubes were amplifiers tuned with capacitor-inductor transformers, often called IF transformers. And I'm going to either assume that you already understand the basics of tuned circuits, or you'll kind of accept a little bit of a hand-waving description intended to keep the video short. The basic idea of a tuned circuit is that at a particular frequency, the characteristics of this circuit reach either a maximum or a minimum. In this particular case, what happens is this particular transformer primary is tuned with this capacitor to a frequency, let's say 455 kilohertz. That's a common frequency of the day. That means that at that frequency, this tuned circuit looks like a high impedance load, and what that means is that it develops maximum signal at that frequency. Similarly, on the secondary, it also is tuned to the same frequency, and it develops the greatest grid signal at the IF frequency. So in other words, at the frequency, if this primary is tuned to the same frequency as the secondary, that frequency will be the frequency that is amplified the most by this circuit. In other words, there will be a big peak at that frequency, and then above that it will fall off. Other than that, transformer coupled or IF tuned amplifiers are basically the same as you've seen before. Generally, there is cathode bias using a cathode resistor, and the resistor is bypassed with a bypass capacitor. In the Philco 384 that we've been using as an example, the IF amplifier is shown here. Its output is tuned with this transformer, and its input is tuned with this transformer. That is a common IF arrangement. In order to convert the signal to the IF frequency, it's necessary that you have some kind of frequency converter. And this is a somewhat complicated circuit, which we will talk about. It's called a Pentagrid converter. But basically it consists of just two things. It consists of a circuit that oscillates at a frequency called the local oscillator frequency, and another circuit that is tuned to the radio frequency, that is the incoming frequency, and the two signals, that is the oscillator and the incoming RF, mix in a tube, usually called a mixer, to produce the intermediate frequency. So let's take a look first at some simple oscillators, and then we'll come back to this particular more complicated structure. Basically, the whole idea of an oscillator is you feed some of the signal from the output back to the input. And some people have described this, it's like a dog chasing its tail. The more it tries to catch the tail, the faster it goes until it just is sitting there spinning at a particular frequency. But basically, a Hartley oscillator is simply a split inductance oscillator. Another circuit, common in the day, was the same thing, but instead of splitting the inductance, you split the capacitance. And that circuit was called a Colpitts oscillator, after, once again, the person who invented it. By the way, the circuit above should really look more like the circuit below. In other words, there should be a radio frequency choke in the B plus line to the plate, and then the feedback signal should be taken off of that. In other words, there is an error in this drawing, and I probably should have corrected that before I started talking about it, or maybe I should have talked about the Colpitts first, because this will not actually produce feedback. You need a way to take some of the plate signal, that is the signal developed across this choke, and feed it back to this tuned circuit. And that's shown down below. So pretend that the circuit above, the Hartley, also has this choke and this capacitor. Now we're going to combine the two concepts, that is the concept of a tuned amplifier with the concept of an oscillator. And we're going to do that using just one tube. And this particular tube is called a Pentagrid converter. Penta just means 5, so it means a 5-grid converter, and a converter is simply a word that means an oscillator combined with a mixer to convert an incoming signal to an intermediate frequency. The circuit consists of the bottom 4 elements, that is the heater, the cathode, the first grid and the second grid are part of the oscillator. We'll talk about that in a second. The next elements are part of the mixer, and the mixing takes place in the electron stream in the tube. In other words, two things are controlling the stream of electrons. One is the input from the control grid. The other is the oscillation of the oscillator. So how does all that work? Well, basically, this grid, even though it is a grid, is not a solid plate, but it's used like a plate. In other words, a positive voltage is applied to that electrode, and the grid is the feedback. This is the oscillator's control grid, and I know this can look a little bit confusing because you apparently have two control grids. The first or lowest is the one that controls the oscillator. The control grid number 4, these are counted from the bottom, 1, 2, 3, 4, is the control grid for the RF signal. So the way this actually operates is this oscillator, that is the cathode and the first two grids with the second grid acting as the plate, it forms an oscillator that is tuned to the local oscillator frequency. This can be either a Colpitts or a Hartley or a number of other variations. In the day, most of these were Colpitts oscillators, but there were a lot of Hartleys used and so on. And then you apply the RF signal to grid number 4. The result is that the electron stream is being varied up and down by the oscillator and is also being varied up and down by the input. The stream, of course, can't tell the difference. It simply reacts to the electric fields. And the result is that the plate current that flows out of here contains 4 frequencies. Frequency 1 is an amplified version of this signal. Frequency 2 is an amplified version of the oscillator frequency. And then, as we talked about earlier, the sum of the two, in other words, the oscillator frequency plus the input, and the oscillator frequency minus the input. It's usually the last, that is, the oscillator minus the input, that is the IF frequency. And of those 4 frequencies, only one is selected by this tuned circuit, and that is the intermediate frequency, and that's passed on to the intermediate frequency amplifier that we talked about earlier. Finally, in better receivers of the day, in front of the converter tube or the mixer oscillator tube or whatever you call this, and different manufacturers call it different things. It can be a Pentagrid converter, it can be a mixer oscillator. Basically, it's the thing that converts the incoming signal to the IF frequency. In front of that, in good receivers, usually was an RF amplifier. This amplifier was tuned to the incoming signal. The antenna would be connected over here. This transformer would then pick a particular frequency, and you may notice that the capacitor here is part of a gang of capacitors. Follow the dotted line up and over and down to here, and then back up and over and down to here, and this capacitor. So this capacitor, and this capacitor are ganged. In the receiver, you will see that as 3 separate sections on the tuning capacitor. So as you tune the radio, if you look inside and you see that there are only 2 sections to the tuning capacitor, that means it does not have an RF amplifier. If there are 3 sections, that means it does have. That's this 3rd section here. This amplifier operates just like the IF amplifier, only it runs at the RF frequency, that is the frequency that you're trying to receive, not at the intermediate frequency. I always like to look at receivers like this in terms of blocks. So if you think of the audio block, that means everything from the volume control to the speaker. That's audio. That is frequencies that you can hear with your ear. You then move back, and in between there is a converter or a detector. The purpose of that is to convert the intermediate frequency into that audio signal. You move back further and you get to the converter tube that converts the RF signal into the IF. So on the left RF, in the middle IF, on the right audio. In the day, almost all of the tube advances that were made But the reason that I emphasize the radio use of electron tubes is not to denigrate the fact that they were also used in public announcement or PA systems, guitar amplifiers, and high fidelity amplifiers for phonographs and other such things. Just that most of the tube development from the early 1900s right up through World War II were done primarily to make better radio receivers. So I hope you've enjoyed this segment. I'm not planning to do any more videos on electron tubes, but if there is an area that is of sufficient interest, I certainly would be willing to consider looking at a specialized area in some more detail. So look forward to seeing you perhaps in some future video, but right now I'm going to get back to the restoration of my SX62A.